For our last time together, I've kind of saved an interesting topic, and that is the topic of VASCAR. It just happens to rhyme with NASCAR, and you'll see the relationship between VASCAR and NASCAR in a few moments here. Anyway, what happens in this video, or in this particular lesson that we're going to be going over today, is something that may happen to you even here on the streets of Selinsgrove. And that is, local policemen are not permitted to catch speeders with radar. They have to use something called VASCAR. Now, the cop who is here in this video is using it. And basically what it is this. They hold something which is like a glorified calculator. And as they see a car coming down the road, when it crosses a line that is drawn perpendicular from side to side, they hit a button. When the car crosses the next line on the highway drawn from side to side, they hit the button again. Then the calculator does a calculation. It knows how far the distance it is, and it knows what time it took between the two buttons being touched. And it gives the officer an approximation as to what the speed is. So this is very personal to me, because a few years ago, I was going over the mountain to a small town called Beaver Springs. And going down the other side of the mountain, there's many switchbacks and real sharp corners and whatnot. As I got to the bottom of the mountain, I became aware of a light flashing behind me, and it was a local policeman. I pulled over. Of course, he checked out my registration and car insurance. And then his first question was, "Do you have any idea how fast you were going?" And I said, "I don't know. Going down a hill with all these corners, maybe 45, 50. I said, "I'm really not aware." He said, "No, you were going over 60 miles an hour, which I was flabbergasted. That's almost physically impossible. But anyway, I took the ticket for the tune of, it was around 150 bucks, something like that. Drove home and was complaining to my wife. And she said, "Well, why don't you do something about it?" And I thought, that's a great idea. So I got a tape measure and I drove back over the mountain. This time I pulled off and I measured the distance between the two lines on the highway that run perpendicular to the sides. Got that distance and proceeded to do a mathematical calculation, okay? Which is what we're going to do today. I'm going to show you that mathematical calculation and how you can do the same thing. And furthermore, how totally unreliable is the technique of VASCAR, okay? So I refuted the ticket, had my day in court, so to speak, and I went into the court, and when they gave me a chance to plead my case, I stood up, presented the judge, presented the officer who pulled me over, he was there, presented them with some documents as to the mathematics behind VASCAR and what really is going on with VASCAR. I could tell right away that the policeman who pulled me over was just like whoosh. I mean, it just went right over his head. He didn't have a clue what was going on. But looking at the judge, I could see him reading what I had done. And I knew as I was talking that he understood what I was saying. But the bigger issue is, that is their golden cow. That officer probably pulls people off all the time, and at the price of the fine, Snyder County is making a huge amount of money in speeding tickets. And there was no way the judge was going to totally excuse me. He did kind of smile when I was all finished and said he cut the fine in half, and I thought, that's probably all I'm going to get, so I paid it and left. But he knew that what they were doing was not accurate or reliable. And that's what I want to show you today. So we'll get started here. Hopefully the computer will run my video.
The two white lines, is it the passing lines or is there other lines?
There's a line that goes across down there.
Okay.
There's a line that goes across up here. What I do is, this machine knows the distance between these two lines as it's programmed in at 0.0569. All right. With VASCAR, the red switch is the timer switch. And what you do is you watch your car, like that pickup truck just hit.
Yeah.
Now the timer switch is on, watching it, and then I turn it off and I record the speed at 44.8 miles per hour. And what the VASCAR does, I know the distance is 0.0569 miles. It told me that that car took 4.57 seconds to travel that distance, and that's how you get the speed. VASCAR is distance over time equals speed.
Okay, now, he said some interesting things. Number one, he's doing it in miles. That's when he was saying the 0.0569, that was the mileage between those two lines. I am going to do it in feet. It doesn't matter, it's about the same amount of work either way. He did say a couple of interesting things. Everything he said was correct, the way VASCAR works. He did say that distance equals rate times time. So R, the rate, is distance divided by time. We're going to do that. And everything we're going to do here is pretty much accurate according to what the VASCAR system is. But I think it'll become quickly apparent what the limitations of VASCAR really are. Okay, so I went back over the mountain and I measured between the lines and I got 100 feet. We are going to assume that the reaction time of that officer is that of a NASCAR driver. Now, folks, NASCAR drivers have been estimated to be the most outstanding athletes in the world because their reaction time has to be so quick to make the proper moves on the racetrack to save their lives and to win the race. But they have unbelievable visual reaction times. So I'm going to assume, to get started here, that the police officer that pulled me over for speeding had the reaction time of a NASCAR driver. Okay? What we want to do is find the range of speeds in this 45-mile-an-hour speed zone and see what happens. All right. So the first thing we want to do is we want to change 45 miles an hour to feet per second. Now, I'm going to write this over here so you can see this. 45 miles per hour. Per means divided by. We want to get rid of miles. We want to get rid of hours. Okay, I'm going to first get rid of the miles. Okay, 1 mile. Put the mile down on the bottom so that the miles cancel. That's 5,280 feet. And then we want to get rid of the hours. The hours on the bottom, I'll put 1 hour on the top. There are 3,600 seconds in 1 hour. Okay, and that's what I have written here. You can cancel the hours. You can cancel the miles. You can multiply the tops, multiply the bottoms, and then divide. And you end up getting 66 feet per second. Okay? Now, because the length between the two lines is only 100 feet, you take that formula, distance equals rate times time, and solve it for time. Time is distance divided by rate. So I'm going to take the 100 feet divided by 66 feet per second, and that gives me 1.252 seconds in between the lines. Okay? 1.52 seconds. If the officer hits the button too soon, like when he sees me coming toward that line, if he just reacts a little bit too soon, and then when I get to the second line, if he reacts just a little bit too late, too soon at the beginning and too late at the end is going to add 0.15 and 0.15, or it's going to add 0.30 seconds onto this, okay? What would happen if on the first line, if he reacted too late, and then on the second line, he reacted too soon? that would be 0.15 and 0.15 at either end that would be taken off of the time, and you'd have to take 0.30 off of 1.52 seconds. His time could be anywhere between 1.22 and 1.82 seconds. Now, when you're thinking about reaction time, I need to tell you what I did on the Monday morning after I got this ticket. I went to my high school where I was teaching at that time. I went to the track coaches. I went to the phys ed coaches, or teachers, pardon me. I got all the stopwatches they had. When my first geometry class came into class, I gave every student a stopwatch. And I simply told them, we're going to watch the second hand on the clock. When it gets around to a 12, I want you to hit your stopwatch. When it gets to the 2, which would be 10 seconds later, I want you to hit your stopwatch. We did this 2 or 3 times. I can't remember exactly how many times we did it. We did it 2 or 3 times, and in the 2 or 3 times, not one student ever hit 10 seconds exactly. Okay? Nobody hit it. It's literally impossible. Okay? Because of reaction time, anticipating, or hitting it too early or too late. All right, so when you take 0.30 off of the 1.52 and add 0.30 on, you get that. Now, let's go back to our formula. Distance equals rate times time. So if you divide by the time, distance divided by time should give you the rate of speed. The distance is 100 feet. I divided by 1.22, and 100 feet divided by the 1.82. Gives me these 2 feet per second speeds that I could be going based totally on the officer's reaction time. Now I'm changing them back to miles per hour, okay? Kind of the reverse of what I did here, because I'm starting with feet per second, okay? So I want to get rid of the seconds go on the top, the hours go on the bottom. So I change them both back to miles per hour, and I get this range, okay? In other words, what I'm saying is giving him the reaction time of a NASCAR driver, 0.15 seconds. He could hit that button and do the absolute best job he can. He can be totally alert, hit the button at exactly the right time, or supposing he thinks so. And due to his reaction time, he could get anywhere in between 37.45 and 55.89 miles per hour. Okay? Which is quite a spread. All right? But what about if his reaction time was normal? A normal adult's reaction time is around 0.25 for a visual stimulus. Let's redo the math and see what happens. Okay? If we repeat the steps, but at a normal reaction time, say 0.25 visual seconds. All right, so let's do that. So what we've still got the 66 feet per second. That doesn't change, okay? Now, if you take the 100 feet divided by the 66, you still get the 1.52. Okay, that 1.52 is because of the 100 feet and the 45 miles an hour. But if the reaction time is 0.25 seconds, what happens if he hits that button just a little too soon at the beginning and a little too late at the end? The 0.25 at the beginning, the 0.25 at the end is going to add half a second, 0.5, onto this and give us 2.02. Okay? What if he then hits it a little too late at the beginning and a little too early at the end? That's going to be 0.25 and 0.25, which is going to subtract off of this and give us 1.02. So now the time range is from 1.02 to 2.02 seconds, okay? We need to take the 100. We need to take the 100 feet again. These are seconds, okay? So we want to get the rate of speed, take 100 feet and divide by 1.02. And I get 98. This is feet per second. Take the 2.02, divide it into 100, 100 divided by 2.02, and I get 49 49.5 feet per second. We'll just call it 49 feet per second. Okay? Now, we got to change it to miles per hour. All right? So I want to get rid of seconds. I want to get hours. I want to get rid of feet, put them on the bottom, get miles on the top. There are 3,600 seconds in 1 hour. In 1 mile, there's 5,280 feet. Multiply your tops. So I'll multiply 98 times 3,600 and equals enter, then divided by the 5,280. And I get 66.82 miles per hour. Do the 49, same thing, exactly the same steps. 49 times 3,600, then divided by 5,280, and I get 33 miles per hour. Now, do you understand how he thought I was going over 60 miles an hour? Okay? Assuming he has normal reaction time, he's doing the best job he can on that machine, but the lines are so close. His reaction time gives him, I could be going any speed in between those two, and he would think it's accurate. Okay? Any speed whatsoever. 66 miles per hour in a 45 mile an hour zone. So, here once again is what we got. The best way to improve VASCAR is to increase the distance on the highway markings, okay? If you increase the distance to the highway markings, it will be much, much better. So let's talk about, I want to show you why. Let's change the distance to 150 feet instead. So we're still at a 45 mile an hour zone. We're going to give him a NASCAR reaction time. We'll give him a NASCAR reaction time. 45 miles an hour is still 66 feet per second, but this time we're going to 150 feet. Divided by 66 gives you an average time of 2.27. If you give him the 0.15 second reaction time, do it at the beginning and the end again. So you're going to add 0.30 on and you're going to subtract 0.30 off, okay, to give this time range, 1.97 to 2.57. Now, we've got to change that to miles per hour. So we know that rate of speed is distance divided by time. So we want to take the 150 now, we changed it, and divide by both of those times. So we have 150 divided by 1.97. I get, let me try that again. I have 150 feet divided by 1.97. Yeah, sorry, 150 divided by 1.97 is 76. This is feet per second. And then the 150 divided by 2.57, and I get 58 feet per second. You've got to change to miles per hour. Okay, you want to get rid of feet again, you want to get miles, you want to get rid of seconds, put them on the top, and you want to get hours. This is 5,280 in 1, 3,600 in 1. Okay, so multiply your tops, 76 times 3,600, and divide by 5,280, and I get 51. Multiply, do the same thing to the 58. 58 times 3,600 divided by 5,280, and I get, actually it was 52. Should round off correctly here. So this is really 52, and then this one rounds off to 40. Just going to 150 feet, okay, you get about 40 to 52. Well, for heaven's sakes, put the small one first, you dummy. 40 to 52. Just going to 150 feet, you get a much better range. It is, even with the reaction time, the VASCAR will work if you make the distance satisfactorily bigger, okay? That is where we're headed for today. Your homework will have you doing similar calculations and trying to find a distance that would even give you a better approximation, because you know you're not going to get a ticket if you're below by 5 miles an hour. If you're above by 5 miles an hour, they won't give you a ticket if you're above by 5 miles an hour. So that's what we're looking for to make this something that is really worthwhile.